All right, let's get started. In this video lesson, we are going to look specifically at physics questions that have appeared on past AP exams. Although you're taking a course on AP Calculus, there is this nice overlap between AP Calculus with physics. And we're going to approach this without using all the velocity and position and distance formulas that you may have studied when you were in physics. We're going to look at this just from the standpoint of derivatives and as well as integrals. So let's get started. First of all, in physics, we talk about these three major ideas. We talk about your position. The units for position typically in problems are going to be meters. Right? And with position, we're discussing location. Then we also talked about velocity, which is a change in your position. It's how much did your position change over a certain amount of time. So the units here typically are going to be meters per second. And acceleration is a measurement of how your velocity is changing over time. So the typical units for acceleration, if your velocity is being measured in meters per second, and your acceleration is a measure of how your velocity changes over time, the units here are typically meters per second, or if you prefer, meters per second squared. First of all, I want to remind you that in all of these physics questions, pay careful attention to the units. If units are given to you, you have to use the units. But you can also use the units as your guide to help you determine what are the right moves you're supposed to make. Now let's go back to this idea of position, velocity, and acceleration. If we start with position, velocity is a measure of how your position changes over time. In previous courses, you might look at delta P over delta P. It's the change in your position over time. This winds up giving you an average velocity over a time interval. Thanks to our knowledge of calculus, we can look at instantaneous change of position. Actually, normally for position, we refer to that as x. And so instead of looking at an average change in position over time, what we're going to do is we're actually going to look at the instantaneous, which is where we're going to talk about dx over dt, the instantaneous change of your position over time. That's a derivative relationship. So if I have position and I want to get to velocity, I'm going to take a derivative. Similarly, we can talk about acceleration being a change in your velocity over time. So if we're doing a dv dt, I want to take the derivative of my velocity with respect to time. That's one way to get acceleration. You can also look at velocity, since velocity is a change in position, and acceleration is a measure of how your velocity changes. We can also look at this. We can say it's d squared x over dt squared. What I really mean by that is that this is the second derivative of your position. That's if we want to move from position to velocity to acceleration. Similarly, if we are at acceleration and need to move up to velocity, we need to undo a derivative. That's where we're going to be doing an integration step. If I'm moving from velocity to position, I'm going to do an integration step as well. So one more time, from position to velocity to acceleration, we're taking derivatives. From acceleration to velocity to position, we are going to be doing an integration step. So what I want to do with this next slide is just look at a really basic example to underscore the difference between position, displacement, and total distance traveled. The question we're going to look at is definitely not a calculus level question, but I just want to set the stage, make sure that we're all on the same page and feeling comfortable with the ideas, position, displacement, and distance traveled. Okay, so here's a little problem that I put together. Again, definitely not at the level of the AP Calculus question. It's a very basic physics question, but let's look at this. My dog Zoe and I recently went for a walk through the neighborhood. We recorded our position at different times along our walk. Time is measured in minutes, and our location represents our position relative to our home. So in the table, we're told that at 0 minutes, our relative position, we are 0 meters from our home. So we are right here at t is equal to 0. After 2 minutes, we have moved 300 meters. So at 2 minutes, we are over here at the 300 meter mark. After 4 minutes, we're at the 900 meter mark. After 6 minutes, we've actually come back and we're at the 500 meter mark. After 8 minutes, we're at negative 300 meters. The way we're going to interpret that is we are, if my position was being measured to the right as positive, at 8 minutes, I'm negative 300. I am 300 meters to the left of our home. And at 10 minutes, we're going to be out here again at the 900 meter mark. So if you want to think about what happened, we started off at our house. We went to the right. Then we continued going to the right. We actually went a little bit faster during that point. At t=4, we had to turn around. And after 6 minutes, we're at the 500 meter mark. After 8 minutes, we're at negative 300, so we had to continue coming this way. And at 10 minutes, we're at the 900 meter mark, so we turn around again and we head back out that way. Yes. Okay, so the first question is asking for my displacement. My displacement is a measure of how has my position changed. Displacement represents change in position. So if that is true, I need to know where was I after 2 minutes, where was I after 6 minutes. At the 2 minute mark, I'm 300 meters away from my home. At the 6 minute mark, I'm 500 meters away from my home. So my displacement is just going to be my position at 6 minutes minus my position at 2 minutes. And that'll tell me that my total displacement is 200 meters. Now let's look at how that question might be different from what was my total distance traveled. Well, my total distance traveled, if I imagine walking with my dog Zoe, we started our house, we walked for a little bit in this direction, we continue walking towards the right, but then we have to turn around and we have to come back. And so starting at 2 minutes, we're at the 300 meter mark, we're walking forward until we reach the 4 minute mark. Between 2 minutes and 4 minutes, my displacement between those two times is going to be 600 meters. That's not what the question's asking. They want to know what was my total distance traveled from 2 to 6. So from 2 to 4, I traveled 600 meters. From 4 minutes to 6 minutes, I traveled back. How far did I go back? I went back 400 meters. My total distance traveled is actually going to be the sum of those two. It's the positive sum. So this is just going to be my 600 meters plus my 400 meters. I went a total distance of 1,000 meters. Displacement just wants to know what's the difference between when I started and when I ended. Total distance traveled, I actually want to know physically how far have I walked, taking into account positive movement as well as negative movement. And we'll see how that impacts our graphs. We could also look at the displacement from t=4 to t=10. I start over here at the 900 meter mark, and I'm going to go backwards to the 500 meter mark. I'm going to continue going backwards to the negative 300 meter mark. From the start of this interval until the 8 minutes into it, I've moved 1,200 meters. Now I'm not done. I then actually went forward. I went from negative 300 to positive 900. So I went a total, I'm so sorry, I was just answering the total distance traveled. The total distance traveled, we started at, so we've got a beginning understanding of displacement and total distance. If I wanted to know my displacement from t=4 to t=10, well, after 4 minutes, I'm 900 meters away from my home. At 10 minutes, I am also 900 meters away from my home. So my change in position from t=4 to t=10 will be 900 minus 900. My displacement is 0 meters. Now, some calculus students will incorrectly interpret that and say that I actually haven't moved. From 4 minutes to 10 minutes, you haven't moved. But if we look carefully, if we consider distance traveled, at 4 minutes, I am 900 meters away from my home. So I am out here. At 6 minutes, I'm back here at the 500 meter mark. After 8 minutes, I'm at the negative 300 meter mark. Already, just in the first 4 minutes of this time interval, I've traveled 1,200 meters. And I'm not done yet. That is just from t equals 4 over here to t equals 8. Now I need to consider the remainder of the interval. I started at negative 300 meters at 8 minutes. I moved forward to positive 900 meters by the 10-minute mark. So that is an additional 1,200 meters. My total distance traveled, 2,400 meters. Okay. Now what we're going to do is we're actually going to look at what's the calculus involved with finding your position, with your distance traveled, with displacement. You might want to refer back to this one a little bit just to make sure that you're really comfortable with the difference between these ideas. Onward to the calculus. A particle starts at position x0, so x is going to represent your position, the 0 represents time 0, so x of 0 is going to represent your initial position. And this particle travels along a straight line with velocity v of t. We're going to use our knowledge of calculus to find each of the following. I want to find the displacement of the particle from time t equals a to t equals b. Displacement, we've already said, is a change in position. If I want to find my change in position from time a to time b, I'm going to take my position at time b. I'm going to subtract from that my position at time a. That's x of b minus x of a. But unfortunately in this problem we don't know a position function. What we do know is a velocity function. Well, what we know is that this is my change in position. And if I use the integral, when I integrate my velocity function I get a position. So I'm going to use the fundamental theorem of calculus, the integral of your velocity from time a to time b. The integral of velocity is position. You apply the fundamental theorem of calculus, which says that you evaluate the position function at the upper limit minus the position function evaluated at the bottom limit. This statement holds true. The other way I like to think about this is I think of it not as xb minus xa is equal to this, but I look at it as x of b, my position at time b, is equal to my position at time a plus my change plus my displacement. So this would represent my starting point. This expression over here represents the change in my position. So if I take my starting point plus my change in my position, I'm going to get my final position. If I want to know the total distance traveled by the particle, well, when we look at total distance, remember we want to consider positive motion as well as negative motion. We don't want those to cancel each other out. So we are going to look at an integral again. We're going to look at the integral of our velocity, but since velocity can be positive, which is forward motion, can be negative, which is backward motion, we want to make sure those aren't canceling each other out. We're going to look at the absolute value of the velocity, also known as speed. We're going to integrate that with respect to t. We're going to start at t equals a, and we're going to end at t equals b. This integral will actually give us the total distance traveled from time t equals a to t equals b. Finally, if I want to know the position of the particle at any time, so we're looking at x of t. If I want to build this function, my position function is going to be my initial position, wherever I've started, plus however far I travel in the amount of time that I'm given. So we'll say it's the initial position plus this integral from 0 to t, v of t dt. If we're given a problem like this, you integrate the velocity. We've already discussed that that is your displacement. My displacement from 0 to time t, if I add that on to my initial condition, my initial placement, that'll give me the position that I'm interested in. So take a moment, jot those down if you haven't done so already, and let's look at an AP problem. All right, so let's look at this problem. This question showed up on the 2009 AB exam. It was question number 6, which means you're not allowed to use the graphing calculator. We've been given a table of values. The top row represents time in seconds. We were given time 0, 8, 20, 25, 32, and 40. We've been given our velocity being measured in meters per second at those time intervals. At the velocity is going to be 3, 5, -10, -8, -4, and 7. We're definitely going to need that information handy. We're told the velocity of a particle moving along the x-axis is modeled by a differentiable function v, where the position x is measured in meters and t is measured in seconds. Selected values of the velocity are given in the table above. The particle is at position x equals 7 meters when t is equal to 0. Another way that could be expressed is my position at time 0 is equal to 7. In part A, we're going to be asked to estimate the acceleration of the particle at 36 seconds. We'll have to show the computations, and we're going to indicate our units of measure. In part B, we're going to be asked to interpret the meaning of the integral of the velocity from 20 to 40 in the context of this situation. And then we're going to be asked to use a trapezoidal sum to approximate that answer. In part C, we're going to be asked if in these time intervals, does the particle have to change direction? And if so, when? And explain our reasoning for that. And then lastly, in part D, we're going to be told that the acceleration of the particle is positive for the time interval 0 to 8 seconds, and then explain why that must mean the position of the particle is at least, at t equals 8 seconds, must be greater than or equal to 30 meters. So let's just jump into this and see what we can do. Part A, we are being asked to estimate the acceleration. We're not going to be able to come up with the exact acceleration of the particle, but we know that acceleration is the derivative of the velocity. That's great. If I actually knew a function for the velocity, we could take a derivative. We could evaluate that derivative at 36. That would give us an exact answer. Well, this is another way that we can look at this. We can look at this as being an average change in velocity over an average change in time. If I want to know the acceleration at 36 seconds, I need to know, well, I do know that at time 32 seconds, the particle has a velocity of -4 meters per second. At 40 seconds, we have a velocity of 70 meters per second. So all I need to do is calculate my change in velocity, which will be 7 minus -4. I'm going to divide that by my change in time, 40 minus 32. 7 minus -4 is 11. 40 minus 32 is 8. Now let's stop before we do anything else. Let's make sure that we include the units. Since velocity is measured in meters per second, my numerator will have units of meters per second. My denominator is time, so it's going to be seconds. Or you could just automatically leap to meters per second squared because you know it's acceleration. And I think that's all we're being asked to do in Part A. Part A is worth 1 point for arriving at the answer 11 over 8. If you use units correctly in Part A and in Part B, even if you don't come up with the correct number, you are awarded 1 point for having the correct units in Parts A and B. And we're going to launch into Part B in just a minute. One thing I want to say before we leave this problem is if I want to find the acceleration at 36 seconds, you might argue, well, 32 and 40, that's nice, but I wanted to use time 25 and time 40. Or maybe somebody else wants to use time 0 and time 40. True, you could use any 2 points on this time interval, to approximate the acceleration. But if you want to find the most accurate answer, then you need to find the smallest interval possible. I'll say that one more time. The smallest interval possible containing t equals 36 seconds, and that'll be between 32 and 40. On to part B. In part B, we're being asked to, using correct units, explain the meaning of this integral 20 to 40 v of t dt. If you remember from previously in the video, if we're integrating the velocity, so we're doing an integral of the velocity with respect to time from a point to a point, this just represents the change in the particle's position. Particle's position from t equals 20 to t equals 40 seconds. That's all that's required for an explanation. This is what it means. It's the change in particle's position. You could also say it's the particle's displacement from t equals 20 to t equals 40. Either of those is perfectly acceptable. Secondly, we're going to be asked to approximate this using a trapezoidal sum with 3 subintervals. And we're told specifically to use the data in the table. So we're looking from 20 seconds to 40 seconds. Before we do this, one thing I want to do, and I think this might be helpful for us, is I just want to plot those 4 points. I'm not going to spend a lot of time making it a perfect graph. I just want to do this really quickly. We have the point 20, negative 10. So I'm going to go to the right, and I'm going to go down 10. 25, negative 8. Go to the right, go down 8. 32, negative 4. There it is. And 47. Those are the 4 points in question. We could connect these 4 points if you wanted to. You don't actually have to. We can just imagine that there is some function doing something. We don't know what that behavior is, but if it helps to get the visual, then I think you should do that. We have these 4 points. We are being asked to approximate this integral. Well, the integral represents the area underneath the curve, or the area bounded by the curve in the x-axis. Starting over here at 20, ending over here at 40. And what we need to do is we need to approximate it. We've been told specifically how to go and approximate it. We need to use a trapezoidal sum. The area formula for a trapezoid is 1/2 the sum of the bases times the height. We're going to divide this interval into 1, 2, 3 trapezoids. Yep. For my first trapezoid, that's going to be this guy over here. We have 1/2. The first base is this length here. We need the y-coordinate, which is negative 10, plus the second base, negative 8, times the height. The height is actually the length of the interval. So from 20 to 25, the length of that interval is 5. When we look at the next one, it'll be plus 1/2. The first base is negative 8. The second base is negative 4. Again, the height is the length of the interval. The interval goes from 25 to 32. So we're going to multiply that by 7. Plus the last trapezoid, 1/2. Your base here is negative 4. Plus the second base is 7. The height, again, is the distance between these. From 32 to 40 is going to be 8. So we have 1/2 times negative 10 plus negative 8 times 5, plus 1/2 times the sum of negative 8 plus negative 4 times 7, plus 1/2 times the sum of negative 4 plus 7 plus 8. When you work that out, you should get negative 75. In order to pick up the additional point for the units, we need to get the unit correct. Since this is position, or sorry, this is displacement, then that means that our units will be negative 75 meters. That's that for part B.